17 countries from all over the world who agreed that they would sign on to this metric system. They would support the International Bureau of Weights and Measures to make this new meter stick, and it would become their standard of measurement. I'd like to point out that the United States of America was one of the original signatories of the Convention de Metre. So we have been metric in your northern neighbor since at least 1875. It just seems that no one has noticed. Well, here's the interesting point. 1875 in France, people were learning how to manipulate light as a wave. And they had learned that by making an interferometer, boy, this doesn't show up too well in the color, but by making an interferometer, interfering light with itself, they could measure length far better than what was possible with a meter. This meter bar, let's see, maybe we can go to the cartoon of the meter. Okay, gotta go the right direction. Here we go. This meter bar has two scratches on it, and the distance between those two scratches is what we define to be 1 meter. It was an improvement over the kilogram of the archives, which was 1 meter between the ends. That's called an end standard, and that's a bad idea, because in order to know where the ends are, you have to touch it. And that every time you touch it, you change it a little bit. Whereas with the scratches, you use a microscope to look at it. The microscope is attached to a lead screw, and in that way you can calibrate your traveling microscope between the two scratches. But the problem with those scratches is they're scratches. Where is the center of the scratch? So it became quite difficult to use the actual definition of the meter to measure something like the wavelength of light. If you move this mirror of this interferometer, then I think maybe you can see these fringes here. This center fringe will change from being dark to being bright if you move this mirror 1/4 of a wavelength. And a wavelength is a fraction of a micrometer. So a few tenths of a micrometer is easily seen on this interferometer, but you cannot tell where the center of a scratch is to a few tenths of a micrometer. You can't even resolve a few tenths of a micrometer with your microscope. So this became a problem, and what people started to do was to use light, the wavelength of light, as a de facto standard of length. That is, everyone agreed that they would express their measurements in terms of the wavelength of light, even though it was not the legal definition of length. And finally, so this was at the end of the 19th century. Finally, in the middle of the 20th century, in 1960, the definition was changed. Now, 1960, by the way, was the year in which the laser was invented. And in that year, 1960, they redefined the meter as being a certain number of wavelengths of krypton, of light coming from a krypton lamp, a picture of which is shown here. And it didn't take very long for people to realize that the purity of the light coming from that lamp was nowhere near as good as the purity coming from a laser. And so people started to make measurements using lasers that were far better than what you could do with a krypton lamp. And so we had the same situation again. Here is an iodine-stabilized helium-neon laser, a gas laser that's stabilized to a certain molecular transition in molecular iodine. And this became the de facto length standard. Everyone reported measurements of length in terms of the wavelength of this laser. But again, it was not the legal definition of the meter. And so we had the same situation as we had before, where people were making measurements better than the legal definition of the meter allowed them to make. And so it was necessary to make another change. And the obvious change would have been to redefine the meter in terms of the wavelength of the light from an iodine-stabilized helium-neon laser. That would have been the obvious choice Fortunately, those people were wise, and they did not make the obvious choice. Instead, they made the brilliant choice. The brilliant choice was to define the speed of light. Why does this give you a meter? Well, by this time, in 1983, it had become possible for people to measure the frequency of light. And this universal and perfect relationship, that the wavelength times the frequency is equal to the speed of light. If we say, the actual official definition of the meter is the length of path traveled by light in a certain length of time. Now, time is very well defined. It has been for a long time. Since about 1967, we've defined time in terms of hyperfine frequency of cesium, and it's really, really good. Time was no problem. This definition effectively defines the speed of light, right? The length of the path that travels, light travels in a certain length of time, call that a meter, that defines the speed of light. So you see, according to this relationship, if the speed of light is defined, if you measure the frequency, you know what the wavelength is. So instead of having a standard that is specific for a certain kind of light, light that comes from a certain atom or corresponds to a transition in a certain molecule, this says anytime you can measure the frequency of the light, you immediately know its wavelength. So that means that when someone improves a laser so that it's more stable, when someone improves the method for measuring the frequency of light, those improvements are automatically incorporated into this definition of length. And so, for example, when people like Jan Hall and Ted Hench figured out how to measure the frequency of light to incredible accuracy, something for which they got the Nobel Prize in 2005, those improvements were already incorporated into the definition of length. So, this definition of the meter, by defining the speed of light, is both brilliant and beautiful. And on the 20th of May of this year, the international community brought this same kind of beauty to the definition of the kilogram, the ampere, the Kelvin, and the mole. So, why did we have to do that, and how is it done? That's the rest of the story. And in order to begin that story, I want to tell you a light history of mass. So, the history of mass goes back a long time. In ancient Babylonia, there were these stone objects, nicely polished, that were the mass standards for that society. One of these stones is something called a shekel, which may be a term that you've heard. And, of course, these standards had the usual problems. From one place to another, they might vary. Something might happen to the standard and damage it, and that would be a problem. And so, again, at the time of the French Revolution, with this spirit of universality, there was a redefinition of the unit of mass. A new mass, called the kilogram, was defined, and it was defined in terms of the meter. The new definition of a standard of mass, the kilogram, was that if you had a cube that was 1/10 of a meter on each side, and then filled that with water, then the mass of that cube of water was a kilogram by definition. Now, turns out it's not so easy to get a cubic deciliter of anything. You know, the meniscus is curved, and the way in which the water wets the surface will change how the water surface is at the surface of the container. It's hard to make a container like this that's perfect. Water changes its density with temperature. The original definition said it should be at 0 degrees at the freezing point. And then people realized, well, that's not so good because the maximum density of water is at 4 degrees, and that would be more stable. And they redefined it at 4 degrees, but it was a problem, and they really couldn't use this definition to define mass any better than a few parts in a million, which sounds pretty good, but they wanted to do better. And so they followed the same path that so many other metrologists had followed in the past. They enshrined the definition into an artifact standard. So they made the best measurement they could of the mass of a cubic deciliter of water, 1 liter of water, and then they made a platinum cylinder and called it the kilogram of the archives, just like the meter of the archives. And they put that in the archives in 1799 along with the meter of the archives, and that became the French standard of measurement. And then, in 1875, remember, that was when we had the Treaty of the Meter, the International Treaty of the Meter. They decided on a new standard, which became known as the International Prototype Kilogram, which was made of platinum iridium. And why platinum and why iridium? These are among the most dense materials there are. And so when you weigh one of these things in air, it has the least correction for buoyancy. The masses displace a little bit of air, and so as a result, the air causes some buoyancy on the mass. And these are the metals that have the least correction for that. So that's why platinum and iridium. And here is a photograph of the International Prototype of the Kilogram right here. Now, let me just go here for a moment. This is the definition of the kilogram. The definition of the kilogram is, it is the mass of that object that you saw under those glass domes. Now think about this. It is now the 21st century. The unit of mass is an artifact made in the 19th century that was based on an artifact made in the 18th century. This, right here, I don't know if you can see that. It's a case that looks very much like the thing that you're seeing projected right now. It is a replica of the International Prototype of the Kilogram. So I brought it so you could see, this thing is not very big. That's it right there. That's a replica of it's the same size. It's not the same mass because it's made out of brass and plated with chromium, so it looks like platinum. That is what the International Prototype of the Kilogram is. And a kilogram is defined to be the mass of this object. If I were to handle it with my fingers and leave a fingerprint on it, all of you would lose weight. Because this is a kilogram no matter what. And so if the standard of mass increases in mass, it can't. Everything else has to decrease in mass. That is scandalous. In fact, it is so scandalous that American comic strips make fun of it. So here's a comic strip from the Washington Post, the hometown newspaper where I live, and it imagines a little girl in her science class, and she's asking her science teacher, "Am I right that we've redefined the meter as the distance traveled by light in this fraction of a second?" This isn't a comic strip, right? I mean, you've just learned that this is the definition of the meter. And the science teacher says, yes, that's because the previous definition based on global differences was imprecise. Absolutely correct. Okay? I love this. And, well, we haven't talked about this, but we've redefined the second, which used to be a certain fraction of the day. It's been defined in terms of the oscillation of the cesium atom. We've heard about that. Yes, very good, he says. So then she says, then why haven't we changed the definition of the kilogram? We haven't. The official definition of the kilogram is still the mass of the International Prototype Kilogram, an actual lump of stuff that's stored somewhere. The somewhere is in Sèvres, which is just outside of Paris, at the International Bureau of Weights and Measures. Why, that's so unscientific. Exactly, she says. What if somebody snuck in and shaved off a piece? Need to lie down. And then she tells her friend, told you there were ways of getting to him. Well, no one has sneaked in and shaved off a piece of the International Prototype kilogram, but nevertheless, its mass is, quote, changing. Here is a plot of a number of other kilograms. You see, when they made the International Prototype of the kilogram, they made a lot of copies. And everyone who was a signer of the International Treaty of the Meter got their own kilogram with a certification of how many micrograms different it was from the International Prototype of the kilogram. Okay? And the International Prototype of the kilogram was the one that was closest to the kilogram of the archives. Okay? So here's what happened to all the other kilograms. Of course, the International Prototype of the kilogram is 0 because it's always a kilogram. And all these other ones are changing. Well, guess what? It doesn't take too much intuition to guess that perhaps it's the International Prototype of the kilogram that's changing. Or maybe they're all changing. And we have no way of knowing what's actually happening because the definition of mass is the mass of the International Prototype of the kilogram. So, how are we going to fix that problem? The answer is we're going to fix this scandalous situation in exactly the same way we fixed the problem of the meter and earlier the problem of the second. We're going to define our unit in terms of some constant of nature. In the case of the meter, it was defined in terms of the speed of light. In the case of the second, it was in terms of the hyperfine frequency of cesium. Which constant shall we use for the kilogram? Well, to see that, let me remind you of what is surely the most famous equation in all of physics. E equals mc squared. So this tells us what the energy of an object at rest is based on its rest mass times the square of the speed of light, which I remind you is defined. Now here's another equation, not quite as famous. It says that the energy of a photon, a particle of light, is equal to the frequency of the light times Planck's constant. Now what I'm going to do is just boldly put those two equations together and rearrange things, and now you see that mass is equal to Planck's constant times frequency divided by c squared. Well, we've already defined c. We can measure the frequency very well, and if we define h, that means we've got a definition of mass. Now, what does this equation mean? It means that if I had some sort of a particle, say a radioactive nucleus, and it emitted a gamma ray of frequency f, then its mass would change by this much. And in principle, I could use that as a standard of mass. We don't because it's not quite accurate enough. But we use this idea that if we define Planck's constant, then we have a definition of mass. And this guy, Brian Kibble, came up with the amazing idea that I'm going to tell you about now for how we can use the definition of Planck's constant to define mass by using an electromechanical device, which we now call a Kibble balance or a Watt balance. And when I first went to the National Bureau of Standards, now the National Institute of Standards and Technology, in 1978, I'm guessing that maybe your parents weren't even born in 1978. but that's what I did. I worked on this Kibble balance. We weren't trying to replace the kilogram, but we had it in mind that maybe this would do it. What we were trying to do was to realize the definition of the ampere. So I'm sure you all remember the definition of the ampere. Well, or the old definition of the ampere. We've got a new one now. The old definition of the ampere was it's the current which, when you put it through two long straight wires of negligible cross-section, infinitely long, 1 meter apart, produces a force of 2 times 10 to the minus 7 newtons per meter of length. That's the old definition of the ampere. That's what an ampere was before the 20th of May. Now it's a certain number of electrons per second. And what we were trying to do was to realize that definition, which doesn't sound like an easy thing to do because infinitely long wires of negligible cross-section are hard to come by. And so instead we were using this new invention of Brian Kibble. So let me show you how this works. Okay, that could work. Let's see. So here. Okay, good. Now, there we go. So So here's a balance. Now, when we want to weigh something, let's say we have some unknown mass, we put some other masses on the other side, and that's what we call weighing, okay? We all know that. But now we might imagine that there's another way of doing it. Instead of using some masses, we might imagine an electromagnet, a coiled wire in a permanent magnet, and we would balance the gravitational force of this unknown mass against the electromagnetic force here. And here's the problem, if we knew exactly what that magnetic field was, and if we knew what the current in this coil was, and we knew exactly where all the wires were and where the current was going, then we could figure out what this electromagnetic force was, and that would be an alternative way of measuring mass. This is the general idea. But here's the problem. It's really hard to take some permanent magnets and know what the magnetic field is. Even if you use an electromagnet, it's really hard to know what the magnetic field is, because while you can measure the current very nicely, it's really hard to know where the wires are, because measuring the position of wires is not easy. And furthermore, you don't know where the current is going in the wire, because when you bend the wire around a coil, it strains it and makes the resistance change as a function of where you are in the wire, and it's really hard to figure that out. So this way of doing things, while it sounds great, is really not so wonderful. But there's a way out, obviously, or I wouldn't be talking about it. Now,